So understand one thing, in this video, we are not targeting to build the most sophisticated AI models that exist to figure out the MNIST dataset. Our target is basically to understand the nuances of building an AI model. We want to understand how to prepare the data. How do we design our model? How do we visualize that model? How do we test it? And then how do we train an AI model? And eventually, how do we use that model to make predictions, right? So that's our entire goal. And now I hope you're excited because this is your very first AI model that you will build from scratch with your own hands, okay? So without further ado, let's get started. The way I would do this is I would watch this video with 1.5 or maybe 2x speed, and then I will come and revisit this video, play it at normal speed, and code along with the video. Okay, this will basically enhance your understanding. Okay, so without further ado, let's get started. So I'm going to open my favorite tool. Can you guess it? Can you guess it? All right, it's obviously the MS Paint, right? So there are three things that are important when you're building an AI network. Number one is data. Data, and data. If your data is not correct, if data is not relevant, it's garbage in, garbage out, basically. Okay, so make sure your data is correct, and therefore we will spend a fair bit of time to understand the input format of the data and what we are doing with the data before we send it to the model. Okay, then comes designing of the AI model architecture, and of course then third one is to train the model. Okay, all right, so that's what we do. Now this is a part of a series video, so if you have not watched these videos, please go and revisit them if you do not have basic understanding of how PyTorch works, what is optimization, what is sigmoid function, what is a loss, how the derivative is taken, and so I have covered all of that in depth. So I will really appreciate if you go and watch those videos first. Okay, brilliant. So let's get started. Let's have a look at, and of course, as usual, I have created this notebook in detail. I'm going to share the link of this notebook, of course. So the data set that we are working. So in this notebook, we will basically build a feed-forward neutral network, also known as multilayer perceptron MLP. And this will be able to recognize handwritten digits from MNIST dataset. Okay. Now, if you don't know what this dataset is, this is Modified National Institute of Standards and Technologies. If I open this, yes, I'm leaving the collab. This is where the data set is kind of stored for you, so you can play around. And if you go back here on PyTorch documentation data set, they have a lot of data sets, right, to play around. We are starting with MNIST, and soon we'll see how we can, go beyond this data set. Okay. Perfect. Our objective of this notebook is to basically create a feed-forward network, train it, and then see if it's able to give you the correct inputs. Okay, we have some input layers with 486 neurons. We will talk about why precisely 784 neurons. We have some hidden layers, and we will have output layer with 10 neurons. We will again talk about why 10 neurons. Okay, the libraries we will use is PyTorch and Matplotlib, because Matplotlib is where we can print or visualize things, and PyTorch will help us understand, or let's say make our life easy to basically build, train, and inference an AI model. Awesome. So first I will do, I'll say clear all outputs. Then again, if you're not sure what this is, how Google Colab works, please go and watch the previous videos. It's really important that you understand the basics of it. If somebody told you that you can watch 2-hour video and you will learn everything about AI, they basically lied to you, right? And I'm here to basically make sure that you learn everything from start to end. So here it is. So I'll press Control Enter. This will basically connect here, if you see on the top right, to a server somewhere on the cloud of Google. And thanks to Google that all of this is free, right? So once it's connected, we're gonna start getting some out. So once it's connected, we're gonna get some outputs. So now let's define some of the hyperparameters. And again, I'm not coding along with you like every single thing because it will take a lot of time to basically design this video. So make sure that you're with me when I'm doing this. So I'm saying some of my hyperparameter HP. So input size is 28 multiplied by 28, which is 720. There's a typo, which is 784. Hidden size is 400, so number of hidden neurons. Output size is 10. Epoch is 10. Batch size is 100. Learning rate is this. So we'll talk about all of this in a moment, okay? So the first thing we want to, let me run this. So we have this in memory. The first thing we want to do is we want to download the dataset. So I'm gonna run this. If you don't know what dataset class is, don't worry about it, because for this, let's say video lecture, you don't have to worry about dataset, but I've already created a video, which basically is on your screen now. It basically talks about what is a data set, how do you create your own data set, how do you use it in a data loader, and so on. So if you're interested, go and watch that. But I think for this video, you don't have to. Just follow along with me, okay? Understand the concept. So this is done. This has been downloaded. So if I go here, now this is my data, MNIST, and I have the raw data, and so on, okay? Brilliant. We will again import data loader as DL from PyTorch, and then we'll say train loader. So this train loader will basically have all the data that we need to train our AI model. So I'll say DL. My data set is basically training data set, which is here. Batch size is hyperparameter batch size, and we have defined our hyperparameter here, and the batch size is here, which is 100. Okay. Shuffle is true because we want to shuffle the data that is coming from the train loader. I think I went a little fast here, so let's go back here. So we are saying that root is data, which means in this folder all the data will be downloaded. I'm saying training equals to true because when you say training true or false, depending on true and false, it will download a different set of data set with different number of items. As you can see, the test set has 10,000 items and the training set has around 60,000 items. Okay. I'm also saying transform this data set. So whatever data I'm getting, transform this to a tensor. Okay. If you don't know what tensor is, again, please go and watch the introduction videos. And download is true because I wanted it to be in my local machine. If you don't say download, it will basically not download anything in the notebook. Okay. Lovely. So let's run the train loader. Let's run the test loader. Now, there are two ways of getting the data out of this loader. Okay. So the first one is that we run a for loop. So this is my train loader, right? So what I'm saying is for train features and train labels in train loader, print the shape of the feature, print the shape of the label, and then break. So all I'm saying is give me one item and then break. So let's have a look what this is, and then we'll see, then I'll talk about what this means. All right. So what, excuse me. What we are seeing here is we are saying from the train loader, we got a batch of data. That's why you see that 100. We get a black and white image. So that's why you see one here. If it was a color image, we would see 3 channels. Since it's a black and white image, we only see 1. 28 and 28 means that the size of the image is 28 pixel by 28 pixel. The train label is 100 because for every image that we get for the feature, we also get corresponding label for it, so that we know that, let's say index 0 is number 7, for example, index 10 is number 2, for example, and so on. Okay. There's another way of getting data out of it. So you can say train loader, iter, and next, and this will give you exact same thing. So if I run this, depending upon the batch size, you'll get 100 black and white images of size 28 by 28. Okay. So far, we have only seen the matrix form of the data. Now let's have a look at how this data actually looks like what it is. So now we're going to visualize the data. You can see we are almost halfway there, so bear with me. You don't have to kind of know about what's happening here, but I'll just super quickly run through it. So I'm saying I need to plot 3 images. So I'm getting train feature, which is basically here, right? It has 100 images of channel 1, which is black and white, and 28 by 28 size. I'm repeating this because data is extremely important when you're doing AI or machine learning for that matter. So I'm saying get me the image and whatever the I count is, so 0 to 3. Torch.squeeze image and dimension 0. We'll see what we are doing here. And then I'm just plotting something. And from train label, I'm pulling out the same index label, detaching it from the tensor, from the CPU, and making it as a numpy so that I can basically create it as a string and then plot it. So if I run this, what you basically see here is I'm printing 3 different images from this train feature, right? And what I'm saying is something like this. So if I go here and I say t1 equal to torch.tensor, and I want the size of the tensor to be 1,28,28, and then if I print this, so we have a tensor, oops, let me say rand, because I want random values in it. So now you see we have a tensor of size 1,28,28. Now this is a little bit too big to visualize. So what I'll say, I will just reduce this to, let's say, 3,3. So now you can visualize this tensor better. So the tensor that we have has 3 rows, so it has 3 columns, which is, let me make it maybe 4, so it's better to visualize. So it has 3 columns, 1, 2, 3. It has 4 rows, 1, 2, 3, 4, and it has 1 set of 4, 3. So if I go here and make it 2, now I have 2 4, 3 matrix, right? Again, all of this has been explained in the introduction video. My humble request, if you have not watched it, please go and watch it. All right. So when I say torch.squeeze, what I'm basically doing is, if I do this and let me make it 1 again, right? If I say torch rand 1, 4, 3, so I have 1 4, 3 matrix, right? So now if I go here and I say t1.squeeze dim equals to 0, now what you should notice is earlier there was 1, 2, 3 brackets, now there are only 2 brackets. What squeeze function does is it basically removes the first dimension, right? So if I go and say shape, now this tensor is of shape 4, 3 instead of 1, 4, 3, okay? Now the reason we are doing this here is because this matplot basically needs a 2-dimensional matrix to basically plot an image, right? And as you can see, the size of the image is 28 by 23, 28 by 20. We are doing all of this, and I'm going a little slow deliberately because if you are watching this video, which means you are new to AI, and this becomes really important to understand what we are doing and why we are doing something. All right, beautiful. Now let's go and design our neural network. So the way we're going to design our neural network is this. We will create a class, we can call it anything, I'm calling it net, which basically inherit NN.module from PyTorch. So every model that you create in PyTorch will basically inherit this as a base class. The structure will be that we will have a linear fully collected layer, we will have a ReLU activation function, another linear, and then we basically say, give me the output, okay? Again, by all means, go and read about it. All right, now let's build the model, and then I'll explain you what we are doing and why we are doing it. So we'll create a class called net. Again, you could create it any name you want, inherits from NN.module. In the init function, self is always there. Then we have an input size, which basically is the number of inputs of the neuron. This is very important, and we'll talk about this in a moment. Then we have a hidden size, and then we have the output size. Okay. So the first thing that you always do in the initialization function is call the super function. Okay. This is basically, it's just a thing you have to do in Python. It takes two arguments, the name of the class and self, and then you call the init. Now we're defining 1, 2, 3, 4 class variables. We're not doing anything with the model yet. Okay. So we're saying self.feedforward network, feedforward1, right, is nn.linear, input size and hidden size. So if I go back here, what we are basically doing is this. I'm saying is give me nn.layer. This layer will have 1, 2, 3 dot dot dot, dot 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 neurons in it, and it will give an output of hidden size. Okay, so now this output could be of any number. We are saying this will be of hidden size, right? Now this in our case is 784. So we are giving 784 input points to this layer, and this layer will spit out basically tensor of size hidden, right? And hidden is basically in parameter. So this is how it will work. Okay. Then we have a ReLU function. What ReLU will do is, once you have this hidden layers, once you have these hidden values, we'll apply a ReLU layer on top of it. Okay. What ReLU does is, it basically ReLU is an activation function which basically changes the input value depending upon if it's positive or negative. If it's positive, it keeps it as it is. If it's negative, it clips it to 0. Okay. Again, all of this has been explained in the previous video, so please go and watch it. So what will happen is, all of this data will go to this function, and you will get exact same number of output from the ReLU, right? Whatever was the input, same output, and it's just that it has been non-linearly activated. That's it. Okay, lovely. Then you have another layer which is feedforward 2 and feedforward 3. Feedforward 2 takes hidden size input and gives another hidden size output. Feedforward 3 takes hidden size input and gives the final output size. Okay, perfect. So we have 1, 2, 3, 4 class variables. We have not used it so far. Now there's another very important function which is forward. Forward is a function which you always use as a forward pass to your model. So when you provide data to the model, this function is called, and whatever it returns is the output of your AI model. So input, forward function, and the output. Okay. Now let's see how we define the forward pass. So we are saying, you can also do it this way, because why not? Let's not make it confusing. All right. So this forward function is basically called whenever you provide data to your neural network. So if I say this is my neural network, and this is what basically we are designing. We are saying we have one input layer, which is FC1. Then we have a ReLU layer. Then we have FC2. And then we have output. Okay. This image is of size 28 multiplied by 28. So length and breadth. We'll provide this data here. You do something, you do something, you do something, and then you give me an output. This output will have 10 outputs on it, right? And whichever output has the highest percentage, so let's say this is 98%. So we would know that the input that we provided was actually 0. If let's say this input was 90%, then we would know that, for example, this image that we provided to this network was number 6, for example, and so on. Okay, this is what we are basically designing and building. So when we say forward, we pass the input to the first linear layer. Whatever the output is, we pass it to the ReLU layer. Whatever the output is, we pass it to the second linear layer. Whatever the output is, we pass it through the final linear layer. Okay, and then we return this value. So let's create this model. Okay, everything is okay. So another thing is we will check if we have CUDA, which is GPU, or if you're working on CPU. So if you go to your runtime, click on change runtime. I'm working on CPU, and I think for this very simple AI model, CPU is okay. But if you're working on a heavier models, it's recommended to have a GPU, for example. And all of this is for free, so big thanks to Google, right? Okay, so we'll run it, and our device is basically CPU. And I've created a function which basically gives me a fresh model. Okay, what I will do is I will just print. I'll print HP so that we know what parameters we are providing. So we are providing an input size of 784, hidden size of 400, and output size of 10. And then we get a fresh model out of it. Again, very critical to understand why the input size is 784. That's because our image is of 28 multiplied by 28. So if you run this, the size is 784. At this point, you should understand that we're doing a very simple trick. And the trick is this. We have an image, right? And this image is basically like a matrix. Okay, let's say this is 28 and this is also 28. What this black and white image contains is basically 0 or 1. I mean, this is very minute level detail, but for example, every cell has some value, let's say 0.23, 0.98, and so on. And the way you can verify this is if you go up where we were visualizing the data. Here, so if I basically take the image, if I say print image, if I run this, you see that it prints zeros and some values. So this value, so whenever you see a very large value, which means this is basically black, and when you see almost zero value, then it's white basically. Sorry, it's other way around. So when you see 0, there's nothing. So this area is 0, this is 0, this is 0. But this area where you have some detail, now this is basically 0.9, 0.8, and so on. Okay. So what we are doing is we take this image and we flatten it out. When I say I flatten it out, means we have 28. So we have an image which is 28. Then we take second row, which is 28. We take third row, 28, dot, 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 and then we take the last row, which is also 28. So 28, 28, 28. Last one is also 28. Therefore, the entire length is 784. So now you understand that my input is basically an image. We flat everything out. Therefore, my input is 784. One single vector or tensor of 784. Okay. Back to code. So we design the model. Now let's visualize the model. So I want to give you a visual feel of how our model will look. So let me install Torch Wiz, and while it's installing, here's my request. If you're enjoying this video, which means that you're learning something, and that is my entire goal. I really want everybody in this world who wants to learn about AI should learn about AI, because this is one of the most powerful things that has happened after internet. And the only way I can achieve my goal is if you can help me a little bit. A small help from all of you who are watching this video will give this channel and me immense power to basically widely spread this knowledge. Okay, so please make sure if you are enjoying this video, if you're learning something, you like the video. Comment on the video if you have any doubts, if you enjoyed it, if you find something that I missed, right? There's always, margin of error, margin of efficiency, right? And lastly, don't forget to share. When you share, YouTube understand that this video creates value, and that way it will be, shown to many people just like you, from Vietnam, from India, from Sri Lanka, and so many, countries which is not America, for example, where people want to learn about AI, but there's no opportunity. So this is your chance to basically give back to brothers and sisters just like yourself. Okay, brilliant. We'll go back. Still installing, but I think we are there. Brilliant. This is done. What I'll do is I'll say here's my dummy input. So I'll just take one image out of the train feature. Again, if you have forgotten, dot shape. Train feature has one grayscale image, right? Which shape is 28 by 28, and it has 100 such images because we are using a batch size of 100. So I'm taking, here's my dummy input, take the first image out of it, send it to device, and then use the dummy input and change it in this fashion. Now again, I have explained this function in the introduction to PyTorch video. Please go back and watch it if you don't understand what this means. What I'll do is I will basically show you super quickly in a very rough way what this does. Okay, so if I have t2 equals to torch.rand, so I'll get random tensor, let's say 4,6, and I'll print it. So we have 6 columns and 4 rows. I could also say t2 dot view -1, for example, and then I can say 8. What it does is, what PyTorch does is, it says, okay, you want 8 columns, so it gives me 8 columns, and whatever the amount of rows, it figures out on its own when you provide -1. Again, go back to the video and watch introduction to PyTorch, and you'll understand what this is doing. So what we are doing here is what I explained to you in this example. So we have an image of 28 by 28. I'm flattening it. So I'm saying, give me 784 columns. I don't care how many rows you have to, create out of it. So I will say, for example, print shape of image dot shape. Okay. And then also I'll say, now I have changed the structure, so I'll say shape of flat image. Now I'll run this. What it will do, it will take the inputs and pass it through the model once, and this is also really great litmus test to understand if you have designed the model correctly. Notice we have not trained the model yet, so it will give you some gibberish output, but if you know what your input is going to be, then you can pass it through the network and you will see some output. And if you don't get any error, which means you have processed your data correctly, you have designed your model correctly, the only thing left is training of the model. Okay, so here it is, and this is a great library, Torch, which what it does is it basically creates a PDF architecture of your model. If you open this, sometimes model is so big that you can't see it on the screen, but when you download the PDF out of it, it's always easier to visualize because you can zoom in, zoom out, and so on. So let's have a look what we are doing. This will be our input, right? Forget about how the gradients are calculated. So all of this mathematics of gradient and differentiation is done by PyTorch. But this is my input, 784. This is my random batch size, which this function has taken. And then there will be feed forward bias, weights, and everything. This is what is happening inside your model. All of this will be provided to the model so that at the end you have 10 outputs, which basically means you will have one of these 10 outputs. And based on the percentage, we will be able to figure out what is the model predicting. Is it number 12, number 8, number 2, and so on. Okay, so you can see all of this here. Lovely. If I can go and print out.shape, this will be 1 and 10, which basically says for this particular input, I think if I run this, You can see that for this particular input, the model thinks that this is we have not run softmax on it. So let's say, assuming we have run softmax on it, let's say this is the highest value. So model thinks the input we provided was actually 0. All right. There's another way of visualizing the summary of the model, and this is basically coming from torch summary. So this, and then you call this function summary, you give your model, you give your input size. So I'm saying the batch size will be something, and then this will be my input size. So if you run it, it will give you a summary of how many parameters are there. So the total parameters in your model is almost 500,000. The ChatGPT 3, I think, from OpenAI has around, I don't know, 10 billion parameters or so, which we will be designing in future videos, so stay tuned. Yes, you will be able to design your own ChatGPT. Just keep following the videos that's coming up, okay? All right, so this is how it is. -1 represents the batch size, so don't worry about it, okay? Now let's define our loss function. So if you go here, we will be using cross entropy loss again. Go back to the previous videos and read through what cross entropy loss means. And when we use this class, what happens is that the data that you saw earlier, this data will be passed through a softmax function. So when I say softmax, that means torch dot, I think nn dot soft. Let's see. There it is. So if I pass this output via softmax function, what it will do is it will clip everything to its percentage value, and if you take it and add everything, so for example, if I say sum, the output would be 1, because softmax will provide, the function will provide percentage to each of these outputs, which is 10 outputs in our case, 0 to 9, and the highest one will have a percentage which we will say, okay, this is the winner. So this is basically equals to what the input image was, and the total sum will always be 1, which is 100%, and that's why you see 1 here. So again, if I remove this, we have 0.1 let me store it to a variable, let's say t3. There are multiple ways of doing one thing in PyTorch. So for example, if I say t3.argmax, what this is saying is the value at the index 0 is the highest, and as you can also verify from here, that 0.1077 is highest among all of it, which basically means the input that we provided to our model here, the dummy data, was actually the image handwritten, which was 0. Now our model is not trained, so it could be just garbage, but that's what it's saying, okay? So we're using cross entropy loss, okay, and as I said, there's a note, cross entropy loss comes with a softmax layer. So when our model, so what we did here basically, additionally we said the output should pass through softmax. When we use this loss function, it will be done automatically for us, okay? Brilliant. So let's run this. So this is our loss function. We'll get a fresh model, and then we will get an optimizer, which is Adam. Again, go and watch the previous video, what an optimizer does. In a nutshell, an optimizer is a way of finding the global minima of the entire model's, let's say, function, whichever way you want to call it. Okay. Lovely. So if you print all the parameters, there it is. So we have 1, 2, 3, 4, 5, 6 layers, and these are the parameters in it. Now comes the training part, most awaited part of it. So we'll say that we will have total training and correct train. So these are two variables which we will track in order to basically see how the learning is happening. We'll obtain a fresh model from this function. We'll define an optimizer one more time. I'm just doing it for the sake of getting a fresh model out of it. It's not necessary. Basically, you can use this one as well. All right. So we are saying for each epoch in hyperparameter epochs, I think we are running for 10 epochs, I believe. Yeah. So we're gonna run through all of our data sets, so 60,000 data 10 times. So all the 60,000 data will be passed through our model. We'll calculate the loss, update the weight. We'll do this 60,000 times. This will be one epoch. Then we'll do it all over again, second epoch, third, fourth, and 10th epoch. Okay, 10 epochs. All of this is basically to track what is the loss and how accurate my model is. The most important thing is here. So the moment I get image from the train loader, I am saying reshape it. Now you should know why we are doing it. Send it to device and send the label to the device. Then we say, this is my model. Pass my images to it and get the outputs. This is where we are actually calling. So if I go back to design neural network, this is where we are calling this function. Okay. So when we give the input X was my images, it will be passed through layer 1, ReLU, layer 2, layer 3, and return the output. Okay. This is happening here. Then we'll say whatever my output is, get the data get the data from it and give me the maximum. So that's my prediction. Then I will say the correct train. So I'm updating the count of correctly predicted sample of this batch. Okay. So again, just to summarize this one more time. When this image is passed through my model will predict this way. One of these 10 outputs. It will have some percentage values. And we will see that if my prediction is actually equals to my label, and label is coming from my dataset, okay? Then based on this, we will calculate the loss using the cross entropy. So this is my output and this is my correct labels, right? Once I have the loss, I'll just, keep adding the running loss. Then I call the optimizer, zero out the gradient. We don't want the previous gradient to impact this loss. Then we say loss.backward. This is where we do the back propagation. Step.optimizer, we say, okay, now take a step ahead based on the loss and optimization. And after every epoch, we basically print everything and then the training is done. Okay, so I'm gonna run this. If you go to runtime, the GPU is provided you for a limited period of time. So before you go and switch to GPU, it's always a good idea to run your loop at least 1 or 2 times. So you see something like this popping up. And as you see, it's for the first epoch. So we have passed through 60,000 images through our model, back propagated, corrected it, and we got 92% accuracy, which is quite good. The second one, it went to 97 and so on. So I will come back once this training loop is completed. The purpose of building this AI model is to basically give you an understanding, a flavor of how an AI model works. And I'm not kidding you, if you open even if the ChatGPT that you see, which is one of the best models that you've seen, it basically follows all these steps. It does a data preparation, cleans the data, makes sure data is ready to be loaded to the model. Then you design a model, right? You test through one of the sample data, you visualize the model, and then you run the training loop. You track the loss and you track the accuracy. And once this is there, that's it. And then you start, testing your AI model if it is predicting the correct values or not. Okay. We have reached 99.2 accuracy, which is pretty good, pretty amazing. And I think that's it. This should be done super soon. So training is completed. Now this variable net has all the updated weights. So whenever you give it an input image, it will be able to predict that it was 0 or 1 or 2 or whatever. Okay. So let's do some testing. So I'm saying with torch.noGrade, which means that now we don't want to train the model. I'm saying image comma label from test loader. Now remember, we had two variables. So if I go back here, we created two variables, train loader and test loader. We used the train loader to basically train the model. Now we're going to use the test loader to test the accuracy of the model. And the important thing is, this data, this model has never seen. So this is the litmus test. Okay, so let's go back here. So I'm saying from test loader, give me image and label. Similar, same thing that you were doing in the training. It's just that we are not doing any loss calculation. We are not doing back propagation and so on. Flatten the image, get the output from it, and then we'll see if the prediction is correct or not. Update the total count of the sample, this, and then we calculate the accuracy percentage, and then we just print it. So let's go for it. It's amazing, right? So it was performing really well in the training section, and it's performing amazing well in the test as well. So you're good to go. So as a bonus, this will come in future videos, but as a bonus, just to understand the concepts, accuracy is really good, but it could be giving us, true positives, false negatives, and so on. So we can also calculate precision, recall, and F1 score. I'm going to run this. I will let you read through it. It's the same thing. From the test loader, we calculate this, and we just apply a couple of formulas to basically see what is the precision, what is the recall, and what is the F1 score. And I've given some commentary here. So all of this is one, which is pretty amazing, right? There's one thing I want to show you as a bonus before we leave for this video. And of course, before the bonus, if you have not liked the video, please do make sure you like the video and share the video. It takes a lot of effort to kind of, design this kind of videos. So I hope you understand that and, return the favor. All right. What I'll say, I will basically do, I'll just copy everything. I will also go to here, visualize data, and I will copy all of this. So what I'm saying is, give me one image, okay? And this time I don't want to calculate any of this. I just want to see what was the image and what was the prediction. So if I go and say print output and label, I think I need to comment this out, and we'll see how we print this. So if I run this, of course there's a batch size attached to it. So we will say outputs of 0 and labels of 0. So I'm saying that it should be tensor 4. Now if you say 0, 1, 2, 3, 4, 4 has the highest value to it. And if you remember, the loss function basically applies the softmax. Since we do not have loss function here, what I'll say softmax equals to nn dot softmax. We'll get this function for ourselves, and then we will pass the outputs to softmax, right? And then 0 is fine, and then I'll say let's run this, and then I'll explain what we can do. So now you see that all of this is basically 0, and this is almost 1. So I will also say dot arg max. So give me the maximum, give me the index of the maximum value. Now you see the index of the maximum is 1 and label is also 1, which means the input image was actually handwritten 1. How can we verify this? We can verify this here. So we will say img equals to images of 0, since we are working on 0 index, and we need this, of course. Then we need plt.im show. I think this should work. Got an error, of course. So before we do this, we also need to say image should be equals to dot view, right, 28, and there you go. I am saying that, let me print it. So I'm saying predicted value is 6, actual value is also 6, and here is the image. Now, I mean, sometimes this could be difficult to visualize, but there you go. So we're saying in predicted value is 8, and actual tensor is actually also 8, and the image definitely says it is 8. And there you go. This is your first AI model that you have created from scratch. So there's a lot of advanced and fancy videos I have planned for this channel for coming weeks and coming months. Make sure you subscribe to the channel, click on that bell button, so whenever I upload a video, you get a notification so that you can go and watch it right away. Thank you very much. EKV signing off. I hope you learned something today.